Greetings and welcome to GILFORD'S lectures. So today we are going to be looking at the question 27 of the Nahpi Physics Entrance Examination question for the academic year 2021-2022. So question 27 reads, if a secondary coil has 40 turns and a primary coil with 20 turns is charged with 50 volts of potential difference, then the potential difference in the secondary coil will be, we are given options A, B, C, and D. So let's dive straight into our solution. So the very first thing I want you to observe here is the schematic diagram showing the different parts of a transformer. So the system defined by this question is a transformer. So this is how a transformer looks like. Observe the different physical quantities associated to the transformer in this question. So the very first thing to take note of is that this is the primary coil of a transformer. This section is the primary coil of a transformer. So we can call this section the primary section, and this is the secondary coil of a transformer, and we can call this section the secondary section. So the voltage associated to the primary section of the transformer is the primary voltage supplying a current I primary through a resistance R1, and the number of turns in the primary coil is Np. Similarly, the number of turns in the secondary coil is Ns. The current in the secondary section is Is. The voltage associated to the secondary section Vs, and this is a resistance R2. But my interest here is to show you how to get the voltage in the secondary section given the voltage in the primary section. So the number of turns in the secondary coil was equals to, so this is Ns. This is equal to Ns. The number of turns in the primary coil was equal to 20 turns. This effectively is equal to Np. The voltage of the primary coil was equal to 50 volts. This effectively is Vp. So at this level, it's important to know that the turn ratio Np on Ns or Ns on Np of a transformer is given by turn ratio equals Np on Ns equals Vp on Vs. Np is the number of turns in the primary coil, Ns the number of turns in the secondary coil, Vp the voltage in the primary, and Vs the voltage in the secondary coil. So we are going to exploit this equation. So we add the number of turns in the primary to the number of turns in the secondary equals the voltage in the primary to the voltage in the secondary coils. If we take the reciprocal of all of these quantities, so here I'm simply taking the reciprocal, I'm going to obtain number of turns in the secondary to number of turns in the primary equals voltage in the secondary to voltage in the primary coils. So if I make Vs object of formula, remember the interest is Vs, I'm going to obtain Ns on Np times Vp. Effectively, when I replace all the above quantities, I'm going to obtain Vs to be equals to 100 volts. So Vs is equals to 100 volts. Okay, so let's move to the question 28. A straight wire of length 0.20 meter moves at a steady speed of 3.0 meter per second at right angles to the magnetic field of flux density 0.1 Tesla. The e.m.f induced across the ends of the wire is, we are given options A, B, C, and D. So solution. So it's important for you to know that the induced e.m.f in a straight wire of length L is given by the formula epsilon is equals to BLV, where B is the magnetic flux density, L is the length of the conductor, and V is the velocity with which the conductor moves in the magnetic field. So when you replace all the above quantities by what was given in the question, you are going to obtain 0.06 volt, and that corresponds to the option B. So question 29. When the work done in moving a particle around a closed loop in a field is zero, the force in the field are called A. Zero forces, B. Non-conservative forces, C. Conservative forces, and D. Viscous forces. So this is the answer. And the reason is simply because a conservative force is one in which the work done in moving a particle in a closed loop is equals to zero. That is, the net work done in moving a particle in a closed loop is equals to zero. Examples of conservative forces are gravitational forces. So we have gravitational forces. Another very good example is electrostatic forces. So electrostatic forces are also conservative forces. We also consider magnetic forces to be conservative. But at higher levels, magnetic force is not a conservative force. Then spring forces are also conservative. So forces existing in springs are conservative. I will take just one example and show you how it is or why it is conservative. So for me to do that, the very first thing I'm going to do is consider a particle at this point and me trying to move the particle in this direction through a height h. So I'm moving that particle through a height h. Then the potential energy given to that particle is equals to negative mgh. So negative mgh is the potential energy given to that particle. The particle is now at this point and I choose to move the particle in this direction. The PE there is equals to 0. So it's equals to, the PE there is equals to 0 joules. The particle is now at this position and I move the particle downwards. The PE there becomes equals to mgh. Remember, I've still moved the particle through the same height as the initial. So the particle is now at this position and I choose to move the particle like this. So the PE there is equals to 0 joules. So remember, the P at this point is 0 joules because there is no change in height. You are simply moving the particle along a horizontal line and not a vertical line. So if we sum all the PEs in this closed loop, so effectively this is a closed loop. That's a closed loop. And if you sum all the PEs in that closed loop, you are going to obtain the net PE to be equals to 0 plus mgh minus or plus 0 minus mgh. All of this is equals to 0 joules. So you discover that the work done in moving a particle in a closed loop is equals to 0 in a gravitational field. That is why we say gravitational fields are conservative fields, or gravitational forces are conservative forces. So let us move to the question 30, which reads: a train with a whistle that emits a note of frequency 800 Hz is approaching an observer at speed of 60 meters per second. The frequency of note or of the note heard by the observer is A, B, C, or D. So you're given the options A, B, C, and D. So solution: the frequency of the note is actually 800 Hz. The velocity of the source is 60 meters per second. The speed of sound is 330 meters per second. Sometimes you may want to use 340 meters per second. So if you use 330 meters per second and your answer doesn't feature in the options, you use 340. So it just depends on the particular value that was used by the examiner. So we want to get f prime, and f prime is given by this formula. But we know that the observer is at rest, and so v0 is equals to 0 meters per second. The speed of sound is c here, and the velocity of the sound was given as 60 meters per second, and the actual frequency f was given as 800 Hz. So when you do your replacement, you are going to obtain 978 Hz, and that corresponds to the option